Hello everyone. For this presentation, we're going to walk through rope rescue systems. What do I mean by systems? These are the different components and operating assemblies of components used for effective rope rescue operations. As far as our outline for this presentation, we're going to start with the core principles of rope rescue systems. Then we're going to talk about how to do safety analysis, build them safely, and go through making sure that the system static safety factor is effective. Then talk through lowering systems, mechanical advantage systems, and then anchors. Objectives of this presentation are to go through the basics of how rope rescue systems operate, gain the ability to analyze a given rope rescue system for how effective it is, select an effective mechanical advantage for a given set of parameters, and then conduct a safety analysis from this system's perspective that we're talking through today. Just a quick note on standards and regulations and things like that that have to do with rope rescue operations. First and foremost, standards and regulations give a good framework for discussing systems and do a lot to give us good uniformity in what our equipment looks like and a lot of how we operate. But it's important to note there are some limitations in how these standards and regulations apply. First and foremost, they don't give specific guidance on how to actually operate a system. Just the same as the motor vehicle code doesn't give specific guidelines on how to depress the gas pedal, how to navigate a curve. Our rope rescue standards regulations don't give specific guidance on how to build a system to give something. They do, however, give just general standards on equipment performance or on necessary areas of competency. So the real relevant standards that we'll talk about, NFPA 1006 and 1670, these are the standards on technical rescue. Standard 1006 is related to individual competency, so there's a level 1 and level 2 qualification under 1006. That's for a kind of basic functioning rope rescue. Then there's a more advanced level, that's level 2, that covers more the operations. Standard 1670 is what covers organizational competency. So this is, you can have an awareness qualified organization or a capable organization or a technician qualified organization, and they give different capabilities for the organizations based on those given standards. So 1670 is about organizations, 1006 is about people. Standards 1983, 1858 are standards for equipment. 1983 is for hardware, things like that. Includes harnesses, things like that. That's what gives you the GTE ratings for general, technical, or escape. And then there's NFPA 1858. That is the standard for life safety rope. That's what gives a given strength and how we know and how we get good quality rope tested to a given standard. Also good to know there are some European standards, some CE or UIAA standards. CE is European, UIAA is Alpine. There's also a few OSHA regulations that apply and some ASTM testing standards that also apply. All not super relevant to what we're talking about. This presentation is going to be focused a lot more on engineering mechanics, how systems go together. Really, these standards aren't super critical in figuring out how organizations can work and how rope rescue systems work super well. All right, important safety caveat. This is naturally an important part of what we're doing. Rope rescue and rope access activities are inherently dangerous, even if the system is properly engineered, built correctly, checked multiple times by qualified professionals. There is absolutely still risk present. You have to conduct rope rescue operations with care, and you are doing so at your own risk. Please follow applicable standards, department SOGs, SOPs, best practices, and use your best judgment in system design and construction. This presentation does not supersede your own standards, does not supersede your best judgment, merely attempting to provide information to help you be more effective in what you're doing. This is not professional engineering advice specific to your circumstances. Recommend that you do your own research, do a good job figuring out your systems, and do safety analyses before you build anything, and trust it with life safety loads. So there's the administrative stuff. Now we'll get really kind of into it. Core principles. It's important to know these. They're a little bit esoteric. It seems like it's fancy, weird math, or like there's no real relevance in this, or this is just purely what you do if you're really bored. But these basic principles do an awful lot to make up the systems and to make the logic make actual sense when we're putting stuff together. So understanding the background, how systems are built, the forces that are at play, how things work together really helps make everything else make sense. And with a good understanding of this background information, just trust me, everything else will make a little bit more sense. There's none of the just rely on some weird simple rule of thumb. Everything's based on reality, and we can talk about that with more specificity. First and foremost for this presentation, we're going to talk about units. And we're going to be very, very clear about what units are used where. I'm not going to use any non-unit given numbers in any calculations or anything that we show through here. For this presentation, we're going to use both US customary and metric units. The reason for this is simple. They have advantages and disadvantages as you look at each one of them. US customary, you can use pounds just and go with that. That's nice and easy. It's actually pretty decent. Then using metric, kilonewtons are a really convenient unit you can use in your head, and that's the given strengths on most of the equipment. The good thing is they're relatively interchangeable. We can talk about that to some more extent. Let's go through the basics. So we have units of force and units of mass that we're talking about primarily for this lecture. I think everyone's familiar with feet, meters, anything like that. If you're curious on that, I'm sure there's plenty of good research out there you can talk about. Force. Force is given either in newtons, which is 1 kilogram moving at 1 meter per second squared, or trying to accelerate at a rate of 1 meter per second squared. For rope rescue work, we're going to use kilonewtons. So 1,000 newtons is 1 kilonewton. The US customary equivalent is pounds, often clarified pounds force, or the LB-F. I'll specify pounds force as much as I can, just to try and be very, very clear that I'm talking about force, not mass. Mass is different than force. We got very used to in the United States of everyone thinking that pounds is force, or pounds is weight, and then kilograms are mass, and etc. That's not really correct. In metric, kilograms are the units of mass. That's given by a certain quantity of material at a given density. So kilograms, and then pounds clarified as pounds mass. The big thing is mass remains constant. An individual can have a mass of, let's say, 100 kilograms. That 100 kilogram mass remains constant even if the gravity where they are is different, or if the forces they experience change. So in a car crash, some textbooks like to say that, oh, heart weighs 1 kilogram, and then as soon as you're experiencing crash forces, it suddenly weighs 5 kilograms because of the rapid deceleration. That's false. It's absolutely wrong. Focus on the distinction here. Mass doesn't change. Force does. Force is equivalent to mass times acceleration. This is given by Newton's second law of motion, and we can use that to describe the basics and how systems operate. So, okay, there's what our units are: kilonewtons, pounds, kilograms, pounds mass, etc. Conversions between the two. 1 kilonewton is equal to 224.81 pounds of force. This is really convenient because average rescuer with gear and tools and whatever, about a kilonewton, all things considered. We round up to 1 kilonewton, round down just a little bit to that 1 kilonewton. So this is really convenient. 1 rescuer is 1 kilonewton. You have a rescuer and a victim. It's a 2 kilonewton load. 2 rescuers, 1 victim, etc. You can do the math relatively easily, and it stays very simple. You don't have to be thinking, okay, this guy's 150 pounds, this guy's 250 pounds, the victim weighs 75 pounds, the Stokes basket weighs 35 pounds. You don't have to do any of that. Just round it all up into kilonewtons and work from there, and your system math works out okay. 1 kilogram is equal to 2.205 pounds mass. If you want to do that conversion, And then what our normal force of gravity that we experience, which is how you convert kilograms to kilonewtons, 9.81 meters per second squared, multiply that times kilograms, then you get kilonewtons. Same applies to convert pounds mass to pounds force. If you're dealing with just an absence of force to begin with, it's 32.17. Generally not necessary. Focus more on, okay, that pounds force to kilonewtons, because we're not accelerating. We're assuming static systems for the majority of our operations. Let's talk about forces in a little bit more of an extent. Handful of different kind of forces. We're talking in classical Newtonian physics, not bringing in strong nuclear, weak nuclear. We're just talking about pure, regular mechanical forces. First is the force of tension. This is force acting to extend a member along its long axis or along any given axis. Example of this, I think we're all somewhat familiar with elastic, for example. You place that under tension, it's storing energy, but you really can't compress stuff that's very good in tension. So tension is the opposite of compression. Compression is acting to shorten or compress a member. This is like an axial load on a bridge column. So heavy stuff on top being transmitted down. Tension is the opposite. If you're hanging a load from a rope, that rope is acting in compression because we're suspending it from above as opposed to supporting it from below. Stress is force acting over an area. So you take one of these force numbers and then you multiply it by the area it is working over, and that gives you stress. So you can have a load that is equal to, I don't know, 10 pounds per square foot. You calculate the area that exists, you have a 10 psf load, you have a stress of 10 psf acting, and then you can calculate eventually the force that is being delivered below that. Useful to know. Strain is the deformation of a material caused by a force. So as you're bending something, you'll experience strain where tension is really happening. That is the material elongating as it gives this ability. A lot more to talk about in mechanics and materials. There's probably some good stuff on YouTube. Go find it. It's cool. Torque is kind of like tension, kind of like compression, but instead it's the weird rotational version of it all. So it is force that is created by another force, and it acts along an axis. So you think about using a wrench to tighten a bolt. You are applying force at a distance away from the axis of that bolt. As you apply that force around that axis, it is moving the bolt down. These moments are a key way we can solve some of these static equilibrium problems and do an awful lot to make sense of complicated systems. So tension, compression, and then think about moments and torque as kind of an extra thing that also exists. Static equilibrium, I think I mentioned that a little bit just before. Any structural system, in general, we can call it stable if it's in a state of static equilibrium. So what this means is obviously nothing's moving, that's why we're calling it static, and we're looking at a structural system, so generally this is an appropriate way to look at it. It's in a state of static equilibrium if all of the forces that act on it are equal to 0. So all the forces in the x direction all sum to 0. So the force of the buttress on one side is equal to the force of the buttress on the other. So forces in the x direction are equal to 0. This also matters with rope systems, because if you're suspending a load and it's not at a perfect vertical, you've got to balance the forces in the x direction with the forces in the y direction. Forces in the y direction are a little bit more obvious. You've got a brick that you set on top of a table, and the table's resisting the brick being pulled down by the force of gravity. It's in equilibrium in the vertical direction. Then we'll talk about the moment also has to be equal to 0. Any rotational forces that are generated away from that given point, those all have to be equal to 0 as well. That can be a little bit more complicated. It matters when systems get really interesting and really complex. As soon as we disrupt static equilibrium, the amount of that disruption is how the system is going to move. So that resultant force vector is what we get as the acceleration once we divide out the mass. So we kind of go backwards from the original Newton's second law of motion to figure out, as soon as we have movement, what's happening. So typical system force is weight. That's the force of stuff being pulled down by the force of gravity. Then we've got normal force, which is the resisting force created by whatever it is, table, ground, rocks, bricks, anything like that. You have a normal force that resists the force of gravity. You have a force of tension that's created as you load something. You can also have friction that exists as a surface is trying to slide against another surface. We'll be more specific about friction. Friction is that resistance to movement that's created by kind of the intrinsic properties of an object. We're all familiar with sandpaper doesn't slide really well against stuff. Like rock on rock has a lot of friction, but Teflon doesn't have a lot of friction with stuff. So these are intrinsic properties to a given material. Friction is created by those intrinsic properties being multiplied by the amount of force that's applied. So you think you can pull, you have a sheet of cardboard lying on the ground on a concrete driveway or something like that. You can easily pull that sheet of cardboard around because there's not a lot of friction acting on it. As soon as you stand on that cardboard, the amount of friction that's going to be experienced increases dramatically. It increases exactly by the amount of the weight that you applied. Friction is very simple that way. It is the force of friction is simply equal to the coefficient of friction multiplied by the force that's applied along that plane of movement. Why is this important? Friction is used in rope systems intentionally to control systems. So photo in the background there, that's an 8-plate figure 8 descender. We are using friction that's created by running the rope through all these bends around the metal to provide control and to slow the descent of a person who's rappelling. We also use friction in soft rope grabs. So the combined multiple wraps of a prusik working with the rope that it's sliding against, there's a lot of friction that exists between all those fibers together. That's how we use them as soft rope grabs. Increasing the friction, though, generally is going to decrease the efficiency of a system. You're going to have to do more work to get less effect. You can see this where there's a nonlinear effect. So you're working really, really hard. The harder you work, the less effective it's becoming because the friction in the system starts to increase. Friction can come from the rope running up against an object. It can come from the pulleys being in poor maintenance, things like that. So be alert to causes of friction in your system unless you're using that friction, obviously, to control movement. So strengths of materials. It's important to know materials have a strength both in compression and tension, and they also have an intrinsic shear strength. So stuff that's strong in tension. Steel and aluminum, pretty darn strong in tension. You can make steel rope. You can also make aluminum cable. All those are very, very good in that axial load. They're also pretty good in a compressive load. But more importantly, we see things like rope and chains as having really high tensile strengths, but they have basically no compressive strength. You can't apply force at the end of a rope towards the long axis of the rope and expect the other end to move. That's just not how it works. If you pull away from the long axis of the rope, like basically pulling rope instead of pushing rope, you're going to be much more effective. So high tensile strength versus no compressive strength. The opposite is true with things like concrete and rock. They have extremely high compressive strength, but they have almost no tensile strength. So you can't make a rope out of concrete, but you're not going to build a bridge column out of rope. They're both very strong, but strong in their own ways. So strength ratings are usually printed on a piece of hardware. So what we have, two examples, that's a locking carabiner on the left, and then on the right, this is a prusik minding single sheave pulley. Both of these, you can see the strengths printed on them. That MBS 41 kilonewtons, so that's minimum breaking strength of 41 kilonewtons, and that's going to be along the long axis of the carabiner. Some carabiners will have it printed as to what the strength is. If you go across the short axis, it's usually much smaller, like 4. And then they also will print the strength if the gate's open. Don't open the gate on the carabiner if it's under load, because its strength when the gate's open is also about the same as if you cross-load it and try and pull it apart in the middle. It's like single-digit kilonewtons versus these 40, 30 kind of kilonewton range. Looking at this pulley, you'll see it has a 36 kilonewton strength at the eye, and then 18 kilonewton strength on both edges of the pulley coming off the sheaves. So you can see it has different strengths because it's figured out differently to take load that way. Then you'll also see a note there, let me get the little pen. You'll see a note, meets NFPA 1983 general use. This means it's in compliance and been tested by Underwriters Laboratories, that's the little mark there, that it meets all of the given standards from that NFPA spec for that strength rating. So there's general use, there's technical use, and then there's escape. Escape is much less common. That's only on some ropes and a couple descent control device type things. You'll see general and technical for most other stuff. Generally means it's good for a large rope system with lots of load, and there's a higher safety factor generally involved in a G system. As soon as you go down to T, the minimum braking strength that's required comes down pretty significantly, but it's still crazy high. We're looking at component braking strength still greater than 10 kilonewtons each, and it's all going to be crazy strong. Don't worry too much about it, but at least it's good to know about. System static safety factor, or just the general safety factor. Safety factor of a system is the ratio of the system's strength to its anticipated load. Obviously, this is very fuzzy and very gray. We don't know the exact properties of materials. We have a pretty good idea that their strength is greater than a given number because we did a lot of testing on a piece of material, and we know that it doesn't break until you hit that given number, and that's a consistent pattern. Okay, cool. So we know the strength, maybe. Load, we have probably even less control over. So how much does the victim actually weigh? Well, we don't know who the victim is. We don't know what they have on them. We don't know how heavy they are. We don't know the loads that the system's going to experience exactly. So this can all be pretty approximate. The thing to do with looking at a safety factor is you have to remember each component of the system has its own safety factor. A given knot, a given carabiner, a given pulley, a given anything in a rope system has its own strength and then the load it is experiencing. The thing is, the lowest safety factor on any component in the system is what dictates the overall safety factor of the system. Literally, what is the weakest link of the chain? That weakest link is the maximum you can load that system because that's what's going to fail. So safety factors can vary. In aviation, we're looking at safety factors somewhere like 1.1. I hear like some rocket construction is done like 1.05. Kind of crazy tight safety factors because they're using a lot of computers and they're using precision materials, being very clean about it. A lot of civil engineering work is in the range of like 1.7, 2.5, things like that. A little bit higher. We're accounting for how little we know about some stuff. Then in a rope system, we're looking at a system safety factor between 5 and 10 as the minimum. So we're going to load this rope with one dude who weighs 1 kilonewton, and we're going to use a whole component of systems that have strengths in the range of 15 to 20 kilonewtons. So we're going to have a huge safety factor and things are going to be redundant. So that 1 kilonewton component or any low kilonewton component is going to be backed up by something else. In general, I recommend you increase the safety factor if you don't know the loads, if you don't know what's going on, or if there's a really complicated system that's coming together. Increasing complexity generally means you should be more cautious and go for a higher safety factor. Departments, organizations, etc. may mandate a given minimum safety factor. This safety factor may be worked out in advance as a part of a pre-rigged system or a pre-drawn out system. It's important to know NFPA doesn't actually mandate any safety factor, so use your best judgment and think this through. Remember that this is how we account for our errors and making sure that we're being safe with our decisions. Now, let's look at another kind of esoteric component of this as well, but this is actually crazy relevant with how stuff actually works. So forces are they're not just a number. Like I can have 3 pens in front of me, but that quantity of pens is just the quantity. Forces are different because they are acting both with a magnitude and they act in a given direction. So, for example, drawn off to the right, what we see is a force acting straight up of 4 kilonewtons, force acting straight to the right of 6 kilonewtons. What happens to an object that's experiencing both of those forces? Well, those forces are summed and mathematically combined for an active summed line of action. So what we see is those two forces acting, they give a total force of 7.21 kilonewtons, and so they're at 90 degrees to each other. They're acting at 33.69 degrees away from that 6 kilonewton force. So as you increase others, you can change the direction of that force vector, or you change the directions of those forces that can change the direction and magnitude of that vector. So why does this matter? We're not building bridges here. We're thinking about how rope rescue systems work. Well, the big thing here is the resultant forces can be higher if you make the angle between them really broad. So you've got to be really careful with anchors and particularly how you're attaching stuff to other stuff. As soon as you bring the angle where things intersect away from 0 and start to make stuff wide and really take it out, you can have a really significant multiplication of force as that increases. So for example, you've got a straight down load, and then you're going to try and balance it between 2 anchors that you're hanging this load off of. You have the option of picking how far those anchors are away from each other, but you're going to keep them symmetric because it's easier that way. If they're not offset from each other at all, so you have a 0 degree angle between them, or an internal angle. If you have a 0 degree internal angle, it's symmetric. The force is split between the two. Cool. Life is good. You can use less robust anchors to make that work. Nice. Now, as we take that further apart, it's important to know that the force that we experience on each one of those anchors increases by the sine of that internal angle divided by 2. Sine is one of the trigonometric relationships. It should be available in the calculator functions of your phone. Feel free to dig in there and do the math if you really want to. What you can do, though, is that internal angle, you can multiply it by the sine of that angle over 2. Multiply that by the force, and you can calculate the force that you're experiencing on those given legs. So as soon as you bring that internal angle out to 90 degrees, you're multiplying that force by 0.7 for what's on each leg. It's not an even split. You're now experiencing more than half of that initial force on each leg. This is because there's forces in the x direction now, in addition to just the forces in the y direction. So it's almost like the load became heavier because you brought that further apart. As you bring that even further apart, so out to 120 degrees, you're effectively carrying the same load on both legs, and that's the same as the load itself. So you've doubled the load effectively as you bring that internal angle out. Why does this matter? You're wrapping a large boulder to use it as an anchor. Boulders are heavy, they're not going to move, that's cool. Especially, guy only weighs 400 pounds down the hill. 400-pound load on that boulder. If you don't use enough material and bring that anchor out to a sharp angle, you're going to run the risk of having all of the load, or basically doubling the load, and seeing it on both legs individually. So be careful with how these forces increase. So that result force, if it's symmetric, is equal to the sine of the internal angle divided by 2, multiplied by that bottom force. Okay, system construction and safety analysis. To build an effective rope system, a couple recommendations, just things to think about and be cognizant of. First and foremost, recommend you plan ahead. Do what you can to think through all this stuff and to think through the scenario itself before you get your heart set on a given tactic or a given set of tools. This is the same as doing a size up on a vehicle crash or assessing the patient before you start delivering care. Same kind of logic here. Don't get too committed to anything before you think through what we're doing. Consider a different approach. Try and avoid using ropes if you can at all avoid it. This happens somewhat often where you'll have vehicle rolls down a hill. Okay, we stop where there's the hole in the guardrail and it's like, okay, get the ropes out, we're going over. There's a dirt road going to the bottom of the hill where the vehicle is resting. A dirt road you can drive the ambulance in on, and this whole operation is going to take 10 minutes as opposed to taking an hour. Remember, the patient's time is more important than yours. Work super fast if we possibly can, but if we don't have to build a rope system, we're saving an awful lot of time. Just drive up to the patient and get him out of there. Next, we'll mention keep it simple. As systems get more complex, the margin for error increases dramatically with each step that we add. There's more carabiners that could be left unlocked. There's more knots that couldn't be dressed right. There's more prusiks that are incorrectly tied. All kinds of errors can crop up as you start adding more components. It's also important to know that a more complex system is going to take longer to set up. It could be potentially harder to operate. Just because you built a fancy 11-to-1 system and you can pull 10,000 pounds with one dude doesn't mean that it's the right thing to do. You've got 8 moving parts, you've got all kinds of complexity going on. Not necessarily what you're trying to do with a rescue operation. You want to be simple, you want to be effective. Then also when you're building the system, lay it out small and then expand it big. So lay out that mechanical advantage in as small of a clean space as you possibly can. Like if you can get a salvage cover out, lay out a small space where you can lay everything out where you can see it in one glance. You can get the system more correct more easily. So consider laying it all out in a very, very small space. Then expand it out to cover that maximum throw once it's all built and all ready to go. So lay it out small first. You can save yourself a lot of time and headache that way. Now we'll talk about doing good system analysis, making sure we've got at least a bit of safety included in what we're doing. 3 key points in doing a good system analysis. And this is a system analysis that we do in advance, that we're doing on an SOP, SOG pre-rigged system. This is not the safety check that is done before using the system. Safety check should be taught later. We'll cover that in different material. That should be covered hands-on as well. We're talking the more in the classroom, in the drawing room kind of recommendations on how a system works together. 3 components to that safety analysis: critical points, whistle test, and then a whiteboard analysis. First, critical points. Look at every component of the system, every knot, every prusik, every pulley, every carabiner, every weird piece of cool hardware you found on the truck. How would a catastrophic failure of that component impact the system? Can it cause a catastrophic failure of the entire system if it fails? So if I remove the rope, for example, the system fails, load falls. Okay, that's bad. So that's a critical point. So we look at each critical point and then ask a set of questions on what we can do about that risk. First, can it be made redundant? Okay, so we've got one rope that goes down to the guy who's on a vertical slope. We only have one rope connecting. Let's put in a second rope. So if the first rope in its system fails, we have a backup rope that exists in a completely independent system, so at least it doesn't fall. Okay, cool. We can make the system redundant. Then we can also look at what are the consequences of failure. So, okay, this one anchor that gives us a change of direction and makes it easier to pull the rope, if that fails, what actually happens to the system? The rope jogs a little bit over and load changes briefly, but nothing happens, no one falls, etc. The belay system's still good, no big deal. Okay, that's not that critical of a point then. We may not actually have to take any action if there are no significant consequences to failure. So if those two really aren't addressed satisfactorily, we can then talk about what is the actual potential for failure of this piece of equipment. Let's say we're using a fire truck as an anchor. What is the potential of it failing as an anchor? I don't know, I'd say it's pretty low. If we take reasonable precautions to make sure that truck doesn't move, it's not really capable of failing. So think about that. Is it even possible for this component to fail? How likely is that to happen? Is that something that we really can deal with as a threat? Then there's the question of would removing that critical point add additional hazard? This isn't super common, but at least it's something to consider of if solving this problem is going to make the situation more dangerous, either think of a different solution or accept the risk and move on. Next is the whistle test. So will the system fail catastrophically, i.e. will the load fall if you blow a whistle, and that means everyone has to put their hands up in the air, put their hands on their head or something like that? Or would the system fail if any one person keeled over and died? Usually the guy running the system, the descent control device or something to that effect. If he keeled over and died, would the system fail? What we're looking for is a fail-safe condition for human error, human distraction, or any kind of human factors as we're working through a rope rescue system. So install components to make sure that the system passes this given whistle test. So what does this mean? It means you have a Prusik ratchet on the descent control device. So if I'm not paying attention and let go of the descent control device and I don't have that Prusik, the rope could just run through freely. If I have that descent control device, or if I have that Prusik on the end of the DCD, it'll catch the load. Okay, guy falls a foot, but no big deal. Have that fail-safe condition if someone is making a mistake or not paying attention, because those things totally happen. Finally, we have the whiteboard analysis. This is doing a detailed analysis where you draw out the entire system, every component, and then work out the forces that are going to be experienced by each individual component. Then compare those forces to the strengths of those components and figure out where the weak links are and if you can do anything to mitigate it. This is an engineering mechanics analysis, going through and making sure that everything isn't exceeding its maximum strength or it's not exceeding the safety factors relation to the maximum strength. Do this in advance of the operation. If you're busting out a pen and a calculator on a scene where there's someone injured, you're wasting your time. You should have done this in advance. Include every component. The webbing of the anchor, the Prusik cords themselves, in addition to the Prusik knots, the hardware, any rope, anything like that. Know their strengths, figure out how they interact for the total system strength and systems effectiveness. Let's talk about the question of a belay or a safety line. Terminology is interchangeable. Belay is a little more climbing. Safety line's a little more some groups. I don't know. Either way, what this is it is a redundant rope and a redundant system that is in place to prevent consequence if the main line fails. So you're doing a vertical operation, you have the main line, that's where the haul system is and the descent control is, that's experiencing all of the load. Then you have a belay line that is separate, independent, run by a different person. So if that main line should fail, gets cut, a piece of hardware fails, the belay line catches them and makes sure they don't fall. Belay lines are simple to set up. It's basically a pulley with a pair of Prusiks on it, or you can use a mechanical device. Basically, all it's there to do is, as rope pays out, if it pays out uncontrolled, the system catches it and they don't fall to their death. So we use a belay when the consequence of the system failure is high. So what does that mean? medium to high angle systems where we're not using the rope to help get up, we're using the rope as our entire support. Any of those systems, you really do need a belay line. If you have a river below, you have a shark tank or some significant hazard that's present immediately below, consider a belay line. Same if you have unstable footing conditions. So for a low angle system, if it's a real loose, not super stable slope, and if that rope goes, you're going to slide the whole way down and it's going to be nasty, use a belay line. Okay, let's talk lowering systems, how we get down to the victim, how we get where we're trying to go. Lowering systems rely on friction to slow and control the descent of a given load. This is us as a rescuer or the patient in a basket with someone tending that litter, etc. So we do this either from the top or at the load itself. If we're controlling it from the top, it's called lowering. If it's being controlled at the load, it's called rappelling. Don't say you're rappelling if you're being lowered slowly by someone controlling the system at the top. It's just bad form. All of these rely on some kind of a descent control device. Descent control can be as simple as running the rope around your arms and kind of slowly coming down a slope with just the friction of doing a good job keeping you from sliding. But really we're thinking more of a proper descent control device. So brake bar rack is kind of the old school one. You got 8 parallel aluminum bars on a big U-shaped tube. You can add or drop bars as you need to add or decrease the lowering capability. You can use a figure 8 device. That's common for rappelling. Some people think it's good for lowering. It's not. Don't do it. You can also use a scarab. That's like a figure 8 and a brake bar combined with each other. That is good for both. And it's a nice piece of gear. Or you can use a mechanical descent control device. So there's the MPD from CMC out of California. There's the Petzl ID or a handful of other of these devices where you have a mechanical control that is doing all of the work for you. You don't have to run it through something and control the friction manually. So there's a scarab on the left side. So this can be used for both rappelling or lowering. So it can be clipped into your gear, it can be clipped into an anchor. Then on the right, that's a rescue aid. So really can only be used for rappelling, not safe, not adequate to use for a lowering system. Lower or rappel. This is a significant question and it depends on your operation. Some it obviously makes sense. If I'm going to lower a victim in a basket down from the cliff they got hurt on down to the waiting ambulance, it's obvious. So lowering is good for a large load, patient, tons of equipment, anything like that. Lowering is a good opportunity. You'll use lowering also if there are few to no obstructions. The big risk here is the guy on the end of the rope doesn't have control over how fast he's going. He doesn't have direct control over how fast he's going. So if there's some weird obstruction, the rope could start to get real slack as he's hung up on that obstruction, and then he can fall. So be very, very cognizant of how that rope is being paid out and the progress that the load is making. It's also real helpful if there's a known target. So you're going to the bottom of a cliff. You're going to the victim location on the side of the hill. The risk here is if you have an unknown destination, you're going to want to rappel. Lowering is also okay if you can communicate with the top side during the entire operation, because they're the ones in control. You have to be able to communicate with them if you're the guy on the end of the rope. Rappelling is more appropriate for a smaller load, such as a single rescuer making initial access. So, vehicle down a hill, first guy on scene can quickly set up a rappel line, throw that rope down, rappel down to the victim relatively safely, and start delivering patient care while a complex lowering raising system is built immediately after that. Rappelling is also appropriate if there's a need to pause and negotiate an obstacle. So if there's stuff in the way that you're going to get hung up on and you know that, you rappel down to that obstacle, lock yourself off, get around it, unlock and rappel and keep going around it. Rappelling is also good if there's an unknown destination. So I know I got to stop somewhere along the length of this rope, but I don't know where, and the guys up top can't see clearly. So I've got to go at my own control to wherever I'm going to look for something. Rappelling is also appropriate for a pick-off rescue. So someone's stranded on the edge of a hill. You can rappel down to them, attach them to your system, and continue to rappel. Or there's a need if the rappeller needs to act independently. So can't talk up the hill, can't do anything like that. Solo or reduce personnel as risk increases, obviously. It's an option to get down to a location. So what does a lowering system look like when it's built? We'll see more system diagrams like this as we go through. Orange is generally going to be the main line. You'll see little arrowheads on there to show direction of movement. Big anchor. There's that descent control device that is attached to the anchor. Then you have a tandem prusik, so that in the event that load falls or you screw up with the descent control device or anything like that, you can capture that load and they don't fall. So have that tandem prusik. Rope pays through the descent control device where we have someone controlling how the load moves down the hill. Nice and simple, easy to build, good system, slow but very effective and very controlled. Lots of opportunities with that descent control device to use different things, but they all fundamentally are built this way. A rappel system, some of that moves down. So anchor and then just the main line coming down, the main line doesn't move, or that main rope doesn't move. The rappeller uses their descent control device to control progress as they move down the rope. This is either by moving your arm up further or by adjusting how hard you pull the handle on the ID. Options like that all exist for how you as the load are controlling your rate of descent. Rappel lines are often backed up with a belay device or a belay system. So belay line's not shown here, but it would extend from the anchor to the load with some variety of a progress capture up at the anchor side. So have a belay line if possible and if it makes sense. It's important to know that the exact configuration of that descent control device is very, very device dependent. So be familiar with what that given device is, be it an 8-plate Scarab, brake bar, rack, ID, anything like that. Some of those devices will pass a whistle test, others will not. So you need to have that belay system for the system to be effective or very safe. Things like the Petzl ID, if you let go, you stop. But with an 8-plate, if you let go, rate of descent is now under no control, so you will fall. So think about that, be cognizant of that risk, and have a belay line if it makes sense. Now we'll talk about mechanical advantage systems. Mechanical advantages are the systems that we use to raise a load against a force, generally gravity. What we're doing is we're amplifying the force that we're pulling by taking advantage of some cool trickery of basic math and being more efficient and more effective in what we're doing. What does a mechanical advantage system look like? We have one over here on the right. It's a combination of pulleys and rope grabs with anchors all working together to move that load more efficiently. We describe mechanical advantage systems by their theoretical mechanical advantage. It's important to know this is theoretical, it's not pure, because there's friction, there's all kinds of other stuff going on. These are their theoretical advantages. 2-to-1, 3-to-1, 5-to-1, theoretical advantages, those are the most common systems that we'll see, and those are going to be what we're really going to talk about. It's important to know that a mechanical advantage system needs more rope. You can rappel 300 feet on a 300-foot rope, but as soon as we're hauling, things get different. You build a 3-to-1 mechanical advantage system, you only move the rope 1 foot if you move it 3 feet on the haul team end of the system. That's because we're doubling back and it's all moving all in multiple parts. We got to account for that though in how we build our systems. So how do we actually make mechanical advantage happen? This seems like voodoo. It seems weird. Just buy into this for a second. Remember what we talked about earlier about static equilibrium and how forces are distributed and how things are equivalent when a system is static and stable. So here we have a nominal system, just 10 kilonewton load attached to a theoretical perfect anchor. The The rope that's between those two experiences a force of 10 kilonewtons. This is all in static equilibrium. There's no forces in the x direction. It's all nice and stable. Everything's okay. So let's add in a pulley and now have that load distributed out between those 2 points. Okay, so what's going on here? 10 kilonewton load down. We're using just nominal math here. 10 kilonewton load down around that pulley being held onto by another force off on the side. That pulley is also anchored. So how does this look? System is going to be in static equilibrium, so the sum of the forces is still going to all end up being 0. But remember, rope has no compressive strength, it only has tensile strength. We're just pulling on that rope. So 10 kilonewtons there, 10 kilonewtons there. Why is that? Because we have to hold that rope as it comes around. We're not holding any of the load necessarily with that. It's all vertical, so we're transmitting that rope is just transmitting force. It's not redistributing it in any way. So 10 kilonewton force then to pull. Let's look at this with something slightly different. Here we have a pulley that is balanced between two equal legs going off at an equal angle. And we'll call it 0 degrees internal angle on the system because the pulley is intersecting at 90 degrees with the ropes. Wherever you are on the pulley, it's at 90 degrees. 10 kilonewton load down. Okay, cool. So 10 kilonewton load on that rope that connects them. What happens now? How is the load distributed between the two? Is it 10 kilonewtons on each rope? 5 kilonewtons on each rope? 20 kilonewtons on each rope? Well, it's a symmetric system, all acting in the vertical direction. We'll assume that there's no angle to those, it's just drawn that way for convenience. What we're seeing is 5 kilonewtons on each leg. Okay, that's cool. Why? Yeah, it's shared between the two. What this means is if I put an anchor here, just an anchor, so I'm pulling against a fire engine that has the ability to resist at 5 kilonewtons, all I'm doing now is pulling on one leg with 5 kilonewtons of force. I produced a 2-to-1 mechanical advantage. So I pull, the effect of my pulling is twice as strong at the end of this system. So simple, it's all because of the statics balancing together and working out like that. So that's how mechanical advantage is developed. Let's look at the actual forces that we get. Average hauler, so a generalized firefighter, can pull between 50 to 70 pounds of force or 0.2 to 0.3 kilonewtons over a sustained hauling operation. So this isn't to make the edge, this isn't like a last hurrah, this is just their general force on the system. So using 60 pounds per hauler, what does this mean each system can produce? If I have one rescuer and I'm pulling just me on a 2-to-1, I can produce 120 pounds, cool, half a kilonewton. Not enough to pull one dude up a hill or up a vertical slope alone. I need 2 people for that because I can't pull that much. So 2 people can generally pull one person up with a 2-to-1. As we go to a 3-to-1, we're able to move that 1.6 kilonewtons. That's a little bit better. 3 haulers, we can move 540 pounds, 2.4 kilonewtons. That is a victim and a rescuer with a little bit of room to be comfortable. So a 3-to-1 with 3 people is a good operating system for the vertical environment. As we have a reduced number of people though, we can use a 5-to-1 and produce 600 pounds with just 2 people. So the math is there if you want to look at it. It's pretty straightforward how it all comes together. Okay, cool. We can produce these forces when hauling. Anyone who's done low angle work will sit and go, there's no way we need, for 4 people at the bottom of a hill, because you've got the victim in the basket and 3 people around him, there's no way that I need 10 people or 4 people, 6 people to make that work. That's not possibly true. So let's talk about how much force actually is required. So force depends on the load and if that load is being hauled up against an angle. What's cool about low angle rescue is the load itself has effectively no friction, because as you pull it up the hill, the legs of the rescuers do a pretty good job not providing a lot of resistance. So you're walking up the hill as you're being pulled up the hill, so it's just weight that you're dealing with. It's not weight plus friction. So if it's a vertical slope, so sheer cliff straight down or negative angle cliff, whatever, we're going straight down, the force that's required is the weight of the load. Obvious and easy. Makes sense, I think, to everyone. Stuff's heavy if you're not pulling it up against anything. As soon as you add that angle, the force that you need is equal to the weight multiplied by the sine of the angle of the slope. So bust out your phone, your calculator, whatever, if you really want to do that math. We can kind of look at it in a general way. So we'll say that 4 kilonewton load of 3 rescuers, 1 victim with gear. What forces are going to be required? 30-degree slope, pretty gentle slope. It's only half as much. So you need 2 kilonewtons of force to move that 4 kilonewton load up the hill comfortably. What does that mean? Okay, so I need 2 kilonewtons. Go back to the table on the previous chart, the previous slide. No, I won't do it. You go back there, you can see how heavy it is. It's not a whole lot. Lower slopes mean less force because you're really just walking with a little bit of an assist. As that slope increases, you get to the 45-degree 1-to-1 slope, 2.8 kilonewtons. So not quite half. It's more like 600 pounds of force. You come up to a 50-degree, 3 kilonewtons, 60-degree, 3.5 kilonewtons. So as you increase that angle, make it steeper, you need more hauling force on the other end. So let's look at the 2-to-1 mechanical advantage. Pretty simple system. This is easy to build and it's easy to keep pre-rigged because you're using the entire rope in the system. Starting at the end of the rope, it's attached to a fixed anchor. Then it runs down to a moving pulley. That pulley is attached to the load. Then the rope comes all the way back up. It is attached to a change of direction, which is optional but highly recommended because this is where you place a prusik to do progress capture, and you have your haul team to pull. This is a good system for low angle operations. Pretty simple to build, easy to keep pre-rigged. The big challenge here, you can't easily change it into a rappel system, or you can't change a single line rappel lower into a 2-to-1. It's not really as possible. You'd have to run the rope halfway down, get it tied off and pull back up. So not as efficient. And the big thing is it takes double the length of the rope because the entire rope is being used for that mechanical advantage because our moving pulley is attached to the load. 200-foot rope means you've really only got about 80 feet of reach down the hill. Not 100 because 20 feet of rope is what you need, at least a few feet to grab for the haul team, a few feet at the anchor and at the edge, etc. So you really only have 80 feet with a 200-foot rope. If you're using a 3-to-1, you have better advantage that way. So 2-to-1s are really common for low angle operation. Stokes with the rescuer is lowered gently without the descent control device. There's a lot of friction, so it handles the load just fine. Rescuers walk down the hill backward to the victim, no big deal. System is ready to go. It's connected and ready to go for an uphaul, and you just pull them back up. So simple, easy, low angle operation. However, we can make it more complicated, more efficient, more effective by increasing it to a 3-to-1 system. So we've added a few parts, but not really. It's still only 2 pulleys. And we've moved the loads around just a little bit in how the system works. So the 3-to-1 mechanical advantage, known to some as a Z-rig, if you're cool, call it a Z-rig, works with fixed end of the load or fixed end of the rope is attached to the load. So carabiner and big set of figure 8s tied in, then you work from there coming up. You have a prusik rope grab, which we'll talk about in a second. Then that rope comes around, runs around to change of direction pulley. This is a mandatory change of direction pulley. Runs around that pulley, then runs into another pulley, and then runs out to the haul team. Haul team pulls on that end. They get a 3-to-1 advantage. They get a 3-to-1 advantage because we have this prusik that grabs onto the rope. So this 2-to-1 we've tied to the main line. We're still pulling on that rope. So we have force that's transmitted here. Then that force is being added onto by more pulled force through here. So you look at the statics, it ends up being a 3-to-1 mechanical advantage system. It's a very efficient, relatively simple system to build. Requires the same number of parts as a 2-to-1. The nice thing with this is a rappel or lower system can be changed into a 3-to-1 pretty easily. So you can have a lot of rope down the hill, tack in this 3-to-1 at the end of it once it's ready, and you can work from there. You can also upgrade this to a 5-to-1 relatively easily. You add in two more pulleys and one more prusik, and you have a functioning 5-to-1 system. It does require a little bit more. You can add in another change of direction if you really want to, but it's more complexity. And it's not as easy to keep this pre-rigged. You're going to want to pay out that load, get the rope down the hill. That's easy to do if you don't have everything else attached, but luckily it's pretty easy to build. It does require resets. So anything other than the 2-to-1, 4-to-1, those simple systems or the pulleys at the bottom, you have to reset this system. As the load comes up, that prusik gets closer and closer and closer to the change of direction. Once you hit it, you've got to stop the system, capture progress, then bring that prusik back out to the edge, and then reset that system and pull back against it. So you'll have multiple resets if you're running a 3-to-1 system. Have a lot of length for resets if you possibly can. Save yourself some time and headache. So 3-to-1s are very good for high angle operations. So any kind of raise then lower or lower then raise, you're going to want to think of 3-to-1. It's probably going to be more of what you're looking for. Gives enough advantage when you have enough people. So a team of 3 can move a 2-person load vertically pretty comfortably. If that gets smaller though, you don't have 3 people available to be your haul team. Start thinking about an upgraded system or taking some friction out of it, make some improvements. So speaking of improvements, we have the 5-to-1. So the 5-to-1 requires 2 more pulleys. So we're adding in a second change of direction pulley and a second moving pulley. It is the same as that 3-to-1, except we're doing the 3-to-1 part, that added extra loop. We're doing that again. So rope starts at the load, is tied on, comes up to a prusik or pair of prusiks. Comes up to that prusik, runs through a change of direction pulley, runs out to a moving pulley. That's attached to the prusik. Then that runs back to a change of direction pulley, back out to a second moving pulley, and then the haul team pulls there. So we have 2 pulleys attached, so you get 2, 4, and then 5. That all is attached to that prusik that's pulling on the rope, and we can be more efficient with fewer people. It only adds those components. Does require more rope to run this system effectively because you've got a lot more moving rope that's tied up in between pulleys. So you'll have to do more resets to make the same progress down the hill because you move 5 feet of rope for every 1 foot of rope you move here, or 1 foot of load movement. It is more complicated. You've got to be alert to how it's laid out. There is a lot of risk because it's just lots of moving parts together. You don't want stuff to get crossed and to be friction against itself. 5-to-1's typical if your haul team resources are scarce. Thinking more like confined space, weird alpine situations where you don't have a ton of people, you don't have a ton of capability, but you have enough hardware where you can make it happen. 5-to-1 with 2 people can move 600 pounds. So 2 people coming up vertically, no big deal. The big caveat again is those more frequent resets. So 5 feet moving at the haul team end for every 1 foot of load movement at the other end. Compound and complex systems. We're not really going to go into that in this presentation, just for simple clarity and staying on message. Compound systems are where you have a simple system and then you're pulling on that simple system with another simple system. So I have a 3-to-1. Then I'm going to add a 2-to-1 to pull on that 3-to-1. That gives me a 6-to-1. They are multiplied like that. They're not summed. that's an effective way to do this. It does require more hardware. It's more moving parts. It's a little bit more complicated. Complex system is, so compound system, you're all pulling in the same direction. So everything's collapsing in the same general vector. Everything's all working kind of in one direction. As we go to a complex system, we have the mechanical advantage that are pulling against one another. So you have a 3-to-1 that you've attached to a 5-to-1 in a different place, and you have the system kind of pulling itself together, which can be extremely powerful. You can build 11-to-1s, things like that, all with relatively little equipment. The big risk here is the system is moving at different rates. So you'll have to reset one part of it before you have to reset the other parts of it, and you can end up with a real logistical nightmare. Also, it can get really powerful. You can have pretty high internal loads. We saw one person can do 200 pounds of force if they're real panicked and pulling real hard, especially if the load is hung and caught on some kind of object as you're pulling it up, and you have that haul team really try and pull super hard. You can generate a lot of force with this 11-to-1 system, enough where you can actually get close to the braking strengths. So things to think about and be careful of. More detail on compound complex systems in training materials. Go to classes on these. These are not easy to cover right now. Notes on system application and how we make them work. First and foremost, start by reducing friction before you try and upgrade the mechanical advantage. Obviously, if you have limited people and you have to build a bigger system, so be it. But try and reduce how things are rubbing against each other before you get crazy and think you have to piggyback the system or do something nuts. Second, leave as much room for resets as you possibly can. Have that if you have the anchor real close to the edge, you have no room to do the resets and to pull. So the further away from the edge you can have the anchor, obviously there's limitations of how much rope you have, how much gear you have. If you can leave as much room as you can make one big pull or just 2 pulls instead of 18 resets. That's just a total nightmare for the people on the end of the rope. So leave as much room as you can. Think about your haul team and the space available in determining what tactic you're going to use. Do I have a lot of room to move? Do I have not a lot of room to move? Do I have 85 people on this scene or more? Do I have like 5, 8 cops who all have gloves and are all wanting to help and want to pull? It's like, that's cool. I can use a smaller mechanical advantage. It takes me less time to set up. Versus if it's me and like 3 other guys, that's it. Don't need a lot of, we'll have to build something more complicated. Also, make sure to check carabiners, hardware, other gear. Make sure that loading is along the strong axis. It's very easy with a mechanical advantage. As you're performing the reset and you're letting the system go slack where you have the moving pulleys, it's easy there for carabiners to inadvertently get cross-loaded while it's slack, and then you start to put some force on it and they'll stay cross-loaded. Be careful. Check your gear, make sure it's working right before you get a lot of load under that system. All right, last but not least, anchors. It's where the systems start, it's where the systems end, and it's got to be effective and work as a system. So good anchors make for safe systems. We know this. Obviously, if the anchor starts to move, good Lord, everything is going to hell. Doesn't matter how well you built the system, but if that anchor is no good, the whole system is no good. Anchors should be strong and immovable. If you want to find some acronym, cool, whatever. Strong and immovable works well for me, and it's something to think about. Anchors should be in line with the intended rope direction. So we're going down the hill. I want my anchor to be lined up with how I want that system to work, especially if I'm using multiple anchors. You want to limit the potential for the rope to swing over as the load changes. Just because I walked off the hill at this one point doesn't mean that that's how the forces are going to balance out and it's going to work. Also, check your anchor for sharp edges, heat, anything that's going to damage it, especially if you're using a human-built anchor, fire engines, pipes, whatever. Make sure you're not like wrapping the exhaust pipe or wrapping something hot, or wrapping something sharp. Tires can be great, going around an axle and working all that as a good anchor. That's a great option. Make sure you're not doing bare webbing on sharp metal. Use edge protection or padding where it's necessary. Same with guardrail. Be careful you're not wrapping sharp bits of galvanized steel on the posts. So what's a good anchor? Vehicles can be really, really good anchors, especially big vehicles like fire engines. Fire engines are good, ambulances are not. Don't use ambulances. Ambulances move once the victim is there, so they're not a great anchor. Fire engines themselves are good. Brush trucks, not as excellent, but they're still pretty good. Large natural objects are great anchors. Big rocks, big trees that are obviously alive and doing great and hanging out. Cool. Fixed permanent anchor points. If you're dealing with some kind of scenario that is in an industrial environment, you can have real anchors that are built in, engineered in place. Those are awesome and the best place to attach if you can. And finally, you can use the structural components of buildings as good solid anchors. Big, heavy, horizontal or vertical members in a building or bridge or something like that. So big steel beams, concrete bridge columns, things like that. Those are all bomber anchors if they can. Obviously, they're taking the loads of trucks driving over them, so they'll be okay with your rope wrapped around the bottom to do something effective. Be careful with these, though. Make sure it's a real structural component. Guardrails to keep people from falling over ledges are not structural. Don't use them as anchors. They won't take the load, especially when you have them up like that. You're going to create a moment because you're putting force at a distance away from the line of action. You're creating a moment. You're going to bend them. It's bad. Don't do it. Same with like bridge rail. Not good. Watch out for those lighter weight bits of stuff. You want the big, heavy, like structural components of things. Vehicles as anchors, being more specific, diving into detail here. They can be very good. You can put them where you want them, which is nice. I want it on the far side of the road, so I'm going to use the truck that's parked on the far side of the road. They're big and heavy. That fire truck is probably heavier than all the force of all those trees' roots working together. And they can have really good attachment points. You can have hitch points at the on the front and rear bumpers. You can have fixed anchor eye bolts like built into the rig. You can wrap the frame. You can wrap the axles. You can wrap tires. You have lots of cool options that give you really, really good attachment points that don't require a lot of brain power to put together. Precautions on these. Don't use a vehicle that may have a potential to need to move. If it's like blocking the entire roadway, it may not be a good option because if someone needs to get around, like an ambulance needs to get around, you may need to move that truck. So try not to use a vehicle that may have any potential to need to move. Don't use a vehicle that is doing something else. So if you have an engine that is blocking traffic, that's not a great candidate to be your anchor because if that gets hit by traffic, suddenly you're moving now with the vehicle that was hit. It may not move very much, but it may move an awful lot. If that rig is being used for things like pumping, being used for fire attack, things like that, I wouldn't use it as a rope anchor. You got too much going on. It's easier to have separate rigs if you possibly can. When you're using a rig as an anchor, set the parking brake. Even if you don't normally set the parking brake on stuff, set the parking brake. Shock the tires. Point the tires away from the hill so that they're, angled away and you have more friction going on. Make sure you have plenty of working space and height. Remove the keys. Take them out. Set them somewhere where there's brain power required to find them. Some groups like to take them, put them in the pocket of the guy who's running the rope system. That's a great way to do it because it's like, hey, where are the keys to this truck? He has to go talk to the guy who built the rope system and who's running it to make sure that's like, oh yeah, no, we're good, we're detached, here are the keys, you can move it. There's also options like consider taking a traffic cone and putting it on the driver's seat to make it like super obvious to anyone who's thinking I'm going to move this truck. Maybe I should think twice before moving it. Same with, you can put a note on the steering wheel, something like that. I've seen like lockout, tagout kind of style things to put over the steering wheel. It can get a little wacky. Something to think about. Make sure that people won't move the truck inadvertently. It's your safety on the line, so take that extra time. Be a little bit overzealous there. Acceptable anchors. So good is kind of my first choice. Then we'll talk second choice kind of stuff. Picket systems are a really good anchor technology. That's what we have on the kind of on the left side. Those are older. This is a set of pickets. They're like big rolled steel driven into some rock. They can be really strong. The big issue is they're time consuming to place. You've got to get them out there. You've got to take big pieces of steel, hammer them into the ground at the right angles, tie the thing together to distribute the load, and then tie into it. So it's good, but it's not as easy as I'm going to clip into a fixed anchor on a truck. Next, guardrail posts can be really good, but there are some cautions. So you'll see the post is actually, it's 6 feet long with only about half of it sticking up. So you've got a lot of embedment in those posts that you can use that make them pretty strong. They're at pretty even spacing, so you can use one for your primary and then use the next one. Big cautions here, make sure they're secure. If they're wood, they can rot out. Kick them a couple times and make sure they don't crumble and collapse and get gross. Make sure there's no breakaway holes drilled in them. As a part of the end anchorages on some guardrails, you're going to have holes drilled in them because they're designed to break more easily. Don't use those, that's bad. Don't use the guardrail itself, the W-beam, the galvanized steel. I don't recommend it because you're pulling in between the middle of posts. It's not super strong in that direction. I wouldn't do it. It's also kind of sharp. The galvanizing isn't finished. They don't go and sand it before they install it, so it can be real sharp and can cut up your rope. Same if they're steel posts as opposed to wooden posts. They can be sharp. Make sure that they're in good shape. So guardrail is a good option. Medium to small trees are a good option too. Oh, one more note on guardrail while I remember it. The other issue with using guardrail, I mean, it's great. The posts are great, but you have no room to work. Unless that guardrail is with some extra embankment space before the hill gets steep and you have a lot of room to work there, guardrail is often real close to the edge. So if you're real close to the edge, you don't have any room to do resets. You don't have any room to run your system and for your haul team to stand and things like that. So there's some challenges if you choose to do that. Good for a rappel line. So if you're going to do a quick rappel down to the victim and to make initial access on a separate rope that's not going to haul and none of that's happening, guardrail posts are a great option. But be careful about that, where they're located before you commit to it for your haul system. All right, moving on. Medium to small trees, pretty good option. Make sure that they're in the ground, make sure they're alive, make sure they're healthy, and that they're not moving if you kick them. Go real low on trees if you can. You're going to want to also consider multi-point anchors. They take more work. They're more complex. You've got to think about the angles that are involved to make sure all the tension back ties are all working effectively. They're a great option if you don't have any really good anchors and you're going to distribute that load between smaller anchors. Finally, you have the option to use climbing style protection. So chocks, nuts, cams, things like that. Things that climbers would be placing as they advance up a rock slope. The big caution here is that these require a lot of experience to place successfully. They can be strong, they can be effective. You're probably going to have to make them multi-point, but they can be the best way you can put an anchor exactly where you want it by using these tools. So take some time if you're going to get into that and study it with experts and practice, obviously before you're subjecting it to live loads. Let's talk about bad anchors. Dead and rotten trees, not a good option. If there's no roots under the tree, it's bad option. Rusty, rotten out guardrail posts that are all just nasty, bad options. Signposts are a bad option. You look at that drawing over to the left, you will see some keywords there that say breakaway. The theory is if someone hits a sign, the sign doesn't basically have the effect of them hitting a brick wall and cause them to be in a terrible crash. The sign breaks and they keep going and it's not a big deal. The problem is if you load this signpost right above that breakaway assembly point, you can shear it off pretty easily because it's just a couple of bolts holding it on. You can have wooden signposts too where you're going to have holes drilled in the bottom that are designed to allow the sign to break easily if it's hit. So don't use them. They're not good anchors. Shrubbery, small plants, random cacti, things like that, not really great anchors, not things I would choose. Making that anchor connection generally is done with tubular webbing, tubular or flat webbing, but tubular is more common. You wrap that object, you attach to that object. There's a few different configurations to do it. Wrap 3, pull 2 is kind of the standard. It's pretty darn strong. You can also do just a single loop around. You can do a girth hitch, different things there. The big thing is making sure that that internal angle stays as small as you can. Smaller than 90 is your goal. If you can get it down to 30 or less, life is good, and you're not overloading things. Tubular webbing has a nominal breaking strength of that 19.3 kilonewtons. That's the standard from NFPA something or another. So that's probably going to be the lowest breaking strength component of your system. So having redundancy in how that anchor is put together, so like a wrap 3, pull 2, you have 2 attachment points that are all coming together as it's wrapped around that 3 times. So you're not, no component in there is experiencing all of the load. And if that one fails, everything's redundant and works well. So think about that redundancy. Remember that tubular webbing is lower strength than most other stuff in the system. So backup anchors, belay anchors, what do you think? What's the deal here? Good question. The decision really has to be case by case on whether or not you're going to back up an anchor or have a separate anchor for the belay line. Consider a backup anchor if you have low confidence in that primary anchor. Low confidence is up to you. If I'm tying into a fire truck, I'm probably not going to back up the anchor because the fire truck weighs like 30,000 pounds. It's not going anywhere because I set the parking brake. It's all chalked. I've got a cone on the driver's seat and I have the keys in my pocket. It's not going anywhere at all. So I have pretty high confidence in that. But if it's something like a tree where maybe I'll put a backup in, and that can make sense. You can do a back tie from that tree to another tree. So you're distributing the load between them. These are options that exist. Also consider a backup if that primary anchor is out of line from the load. So if there's something that's about to happen where the load could swing and you're going to create a dynamic load in the system, it's something to think about and be cognizant of. Belay anchor is going to be warranted if that primary anchor is doubtful at all, or if you don't have a good second place to tie on to that primary anchor. What I mean by that is your main line, you're attaching to a rigging plate. That rigging plate is attached then to the anchor. Don't run the belay off of that rigging plate if you can at all avoid it. So you'll use another attachment point on the engine, another guardrail post, something like that. If you're at all doubtful of that primary anchor and its attachment, so any natural object, any weaker components that are showing up there, you're going to want to have a separate belay anchor that is a little bit off of all that. So if something goes wrong, it's entirely isolated and it'll be okay. So you have the option to consider a distributed loading system, pre-tension, back tie, anything like that. There's a lot more to learn on that, and it's all pretty cool if you want to get into it. All right, so getting close to 90 minutes, so we'll get wrapped up here with some concluding thoughts. Building that effective rope rescue system. First and foremost, plan ahead. Think through what you're trying to do. Am I getting a victim picked up from the bottom of a hill? Am I making access to a weird location? Think about the configuration of the terrain, the location of the victim, what all of our options are before you get your heart set on any tactic or set of tools. Think about the loads. How heavy is this going to be? How many people do I have with me? What can we do? Do your best to avoid using ropes if you can at all avoid them. If you can walk to the victim and it takes a little bit, and it's a little bit of walking out of direction versus just throwing a rope and doing that, do the walking. It's going to take less time. It'll be easier and it'll be safer. Second, keep systems simple. The more complex they are, the higher your margin for error. The more complex, the more time they take to set up, and the more complex they are to operate. You can have multiple things moving in multiple different rates, and it's a total pain, it's a total mess. Keep it simple if you possibly can. Finally, lay it out small, then make it big when you're done. Lay that mechanical advantage space out in as small of a space that you possibly can, especially if you can see all of it at once. Put it all on a single tarp, lay it all out nicely, make it super clean, make it look as good as a photograph in a manual. Okay, now that it's built, checked, everything's ready, then expand it out and make it ready to go. This reduces your chances for errors. Make sure your system's built right. It's easier and it's going to be more straightforward. So lay it out small, expand big. All right, there we go. Close to 90 minutes on rope rescue systems. Basics of how we put stuff together, what the forces are, how they work. This is not a substitute for hands-on. Got to go spend some time out there messing around with these, building them, and getting used to it. Just want to give a good classroom introduction on what a good system looks like and how it functions. Thanks, everyone. Put any questions down in the comments, description thing, whatever. I'll do my best to answer them, think through it. Otherwise, y'all stay safe, do a good job, build good systems, anything like that.